Hello and welcome to the 109th IUVSTA workshop, the APPEC Technology Forum Vacuum Cryogenics, where industry meets academia. Today, we will have a short teaser by one of our invited speakers, Bianca Bottino, who will report on the search for dark matter WIMPs with the DarkSide experiment.
Hello again to everyone. I'm Bianca Bottino, and I work on the DarkSide experiment for dark matter direct search at LNGS, so at the Gran Sasso National Laboratories. And I will give you a brief overview of what I'm gonna cover in my talk. So I will discuss a little bit the scientific goal of the DarkSide program, and then I will enter into more details about the DarkSide detector, and in particular, I will focus, of course, on the cryogenic system. So the DarkSide-20k project, it's a huge program that it's based in Italy at the underground laboratory of Gran Sasso, and in particular is under construction at the moment in Hall C. So what you can see on the left side of the slide in the picture is actually the external membrane cryostat that will host the dark matter detector that will be equipped with two sorts of cryogenic systems. So in particular, the DarkSide detector has a nested structure. So the innermost part is a time projection chamber, so what we call for short a TPC, that will be made of ultra pure acrylic, and this will be basically the target for the dark matter interaction, and it will be filled with liquid argon. Actually, it will be a dual phase TPC, so it will be mainly liquid argon with a small layer of gas argon at the top. And the TPC will be viewed, so the active volume will be viewed by two layers of cryogenic silicon PMs, so photosensors that will be basically at the top and at the bottom of the volume. Then the TPC is actually surrounded by a neutron veto, which is necessary to get rid of a very nasty background induced basically by neutrons. We will see more in details what this means during the real talk. And the veto is also equipped with cryogenic photosensors and uses as active target liquid argon. So these two detectors are enclosed in a stainless steel vessel, which separates two different volumes of argon. So the innermost is what we call underground argon, and I will come to this in a minute, while the outer part of the detector, so everything that sits outside this stainless steel vessel, is atmospheric argon. And this volume, which is enclosed in this red membrane cryostat, will host also muon veto. So this is roughly how our detector looks like. And one of the key points of DarkSide is the use of two different argon flavors. So what we call underground argon is a special kind of argon in the sense that is extracted from deep underground sources. In particular, we extracted in Colorado with a plant that it's actually being commissioned in these days, that it's called Urania. And then this argon is sent to Sardinia, where we have a special distillation column that can reach very high purity, which is needed in order to have a very low background experiment. So in the bottom right picture, you can see the prototype column of the ARIA plant. And then we have also a special facility to actually measure the radiopurity of this special argon, and so the depletion factor in argon-39. So how much we can reduce argon-39, which is a radioactive isotope that induces a dangerous background for us, and that it's the reason why we need this special argon for our innermost part of the detector. The outer part is filled with atmospheric argon, which is the regular argon, so commercial argon of regular purity, that it's needed actually to guarantee a thermal bath and also to install another part of our detector. So these two argons cannot, of course, be mixed because the key point is to not spoil the purity of the underground argon. And we will see why the underground argon is cleaner, let's say, with respect to the atmospheric one. So why we extract it from there. But the key point is that we cannot then mix together the two. And so we developed two separate cryogenic systems, and we will get into the details of both of them, with a special attention to the one for the underground argon, which is a completely custom-made cryogenic system based on liquid nitrogen with a cooling power of roughly 8 kilowatts and with a very high recirculation speed to guarantee to keep this purity for the whole running of the detector. And on the other side, we will also have a deeper look into the so-called proximity cryogenics, which will serve to basically liquefy and purify all the 700 tons that will fill the huge membrane cryostat. So this is basically what I'm gonna talk about, and thank you for your attention.
Thank you for listening to the short introduction to topics of our 109th IUVSTA workshop, and we hope we can welcome you in Maastricht at the meeting on November 24 to 26.